And there we are. Good afternoon, Jan. How do you do?
On this side, everything all right? What about you?
Excellent. Doing well. Very well.
I
It's
expected to see a whiteboard behind you.
oh, yeah, it's fallen down. I hadn't even noticed that.
No,
Yeah, just a blank space where it used to be. Yeah,
that would be nice to make some drawings, some diagrams.
yeah. The big whiteboard is off camera. That's where I do most of my thinking.
Okay, that
It,
must be a very big one then.
yeah, yeah. That small one, you just handheld thing.
Hmm.
Um, I actually used that for uh, the newsletter. So I had a just a whiteboard drawing of something, usually a diagram that was at the header of the newsletter, and so I just drew something real quick, typed in a thought, and pushed that out there.
And which newsletter was that?
That was the one that I started just around the launch of the book. I started it just a little bit before. That's actually um, where I first announced
Yeah,
this
yeah,
get
yeah,
together.
yeah. But that newsletter is not going on anymore.
No, no, I
Oh,
I
okay.
kept that going just a little bit after the launch of the book.
Hmm.
Um, yeah, that was the intent was to just to kind of um, to drum up a little bit of interest around book launch,
Hmm.
and uh, and so yeah, um, that was the commitment I made with that, and so keep this going,
It worked.
and
It
yeah,
worked. I'm here.
yeah, exactly.
Uh, no, I had this this nice paper now,
Excellent. Yes.
which is a very nice. It's much more detailed than the previous one you made,
Yes.
um, and very interesting. But it gives me, it helps me, but it gives me headache. Um,
Well, yeah, yeah. So I'd like to spend some time going through that today,
mm,
and uh, and just see where it can be improved, what questions you've got, that kind of thing.
mm. Actually, the meeting from last week should be the sequence of this one
Yeah,
about the feeds, and because that was really interesting, where we walked through the protocol, especially the first time that we really saw it working
hmm
in real life. Um,
yeah,
and this paper also is interesting.
yeah, yeah. This paper kind of it talks about that that protocol being there, but it doesn't go through in a lot of detail. So yeah, it talks about that there's a feed query and there's a results
Mm.
query, and the feed query uses a bookmark, and the bookmark is um, a
Oh,
a
Ray.
sorted array of integers. That's it. That's all you need to know. But why? And we talked about yesterday or last time why it's a sorted array of integers and
Mm.
yeah, all that stuff. So yeah, there's probably a whole new book in the implementation of Jinaga that proves that a sorted array of integers solves the problem with bookmarks.
Mm.
It proves uh, the the query inversion algorithm that I'm using now, which is different than the one that I presented in this book. Um, yeah, there's a lot of improvements since the original book that
Mm.
made it into this implementation.
But it's amazing the way you came to this the structure o- that you found to solve to generate
Yeah.
first the specification language, or the link language, then the specification language, then transforming that into SQL. There is really a structure behind it.
hmm
Um, There must have been a lot of sleepless nights into that.
Yeah, I usually listen to podcasts on the way to work and the way back, but when I have one of these algorithms to kind of go through, I'll just not play the podcast and then um, I'll just reason through the algorithm on the way home or on the way to work and so yeah, usually by the time I get there, it's like, oh yeah, I could prove that um, and then I've got a structure and I can start from there.
Mm.
Yeah, yeah, and
That must be
it
now.
was
Now I've
yeah, it was really cool
now I
that
have the.
the structure that you talked about. The link created the query language, and then the query language created that observation that
Mm,
the way that I had been um, talking about queries as a pipeline was a serious restriction. That's where the idea of having only one input started from. Having multiple inputs in that kind of a system is a little bit harder to reason out. But then that also made inverses much easier to see it in this structure. So the idea of satisfying a set of conditions on a set of labels simultaneously, um, that's that just makes both of those operations
mm,
much nicer, and then that um, that leads to the result being a collection of tuples. So each tuple is a simultaneous solution to all of those constraints, and then
mm,
yeah, now you can reason through that for any given uh, set of data, for any given subgraph of the possible states, you can define a single finite set of tuples that specification means, and then you can pick out which ones you want to filter on, and those become the inputs. So now you can change your inputs to these three, swap it over to this one, and then that you just did the inverse. So it's
mm.
it makes things a lot easier.
But just now you found the explanation why you understand it and I don't.
Oh.
Well, you drive to work and I work from my office here,
There we go.
so
Yeah,
I'm not driving. So uh,
yeah, yeah. You
must
need a commute, and
that
then
that
you'll get a lot more done.
no, if that would be the reason. Okay,
All right.
let's start with it.
Yeah, so I will do a screen share so that we can capture this. And so I'm going to at first share the GitHub version. So I'll go to the SQL Generator docs branch. Come on, GitHub. What are you doing? There you go. And then under docs, SQL, we've got SQL Generator IPYNB, which will now be my default format whenever I create any new notebooks, because it saves the results, and GitHub can render the document with the results. So much nicer. Okay.
Did, did you find a way to print that out in a nice way? Because
Yeah. Um, yeah, I haven't
I
tried the print.
I had to load an extension into Edge
Hmm.
to make it visible into Edge, and then print it out from there. But normally in VS Code, you can the Jupyter output, you can export it into a PDF.
Mm-hmm.
But that's not working in my case. I don't know. I don't know why. But
Hmm.
it's such a nice format. But printing, they forgot about it.
Huh. Yeah, that does seem strange because IPYNB Jupyter notebooks are intended for creating papers, and so it seems
Yeah.
that printable export would be feature number one. Um, yeah, I haven't researched that. So
Just working
Huh.
with that extension in the browser, so it renders it in the browser, and then you can print it. But it was not built in.
Hmm.
I found that strange.
Okay. Oh, I haven't switched to the. There we go. Now everybody on the stream can see the document.
I
Okay.
have it on my screen, the document.
Okay. Yeah. So let's go ahead and start with. So we've got an overview of the specification language that starts with a description of a very simple model. Um, and as you recommended before, um, for this document, I made the model just a little bit more complex at each step and added a little bit more complexity to each of the specifications, as opposed to in the first one, I started with a single specification that demonstrated all of the features.
Mm-hmm.
So this should be a little easier to follow along. So it starts with a school offering courses, very simple two-fact model. And then we've got some example data that I load in there for Math 101, Math 102, 201, and 301. And they are
Michael, I
all
think
offered by the same course. Mm-hmm.
it would be useful to enlarge a little bit, to use the full width, because the text is hardly readable.
Okay.
Yeah, that's much better.
Yeah.
That's okay.
Yeah, thank you. Yeah. So, yeah, all four offered by the same school. And we can also see the name of the role indicated on these diagrams. So that becomes an important part of the SQL that's generated. So then we put together um, our first specification. So in link, that's just from course in facts of type course or course to school. Select the course. So that's um, the keyword syntax for that link query. And then just run that on the data that I put in there, and it kind of just spits out those school or those course facts. So a course has you can kind of see the summary at the top. A school, which is equal to the school that has the name LPS Frisco and the identifier Math 101. And then here it's broken down into where you can see school is a separate object with a name property and the identifier is another property. So it's just a very explicit way of showing those objects. But then here, you're keeping in the point of the paper is to show the specification language and how that translates to SQL. So converting that to specification language, we get given a school, find all course where course school is equal to school, and you can see the types clearly indicated inside of that specification language. So that was, just as an aside, putting the types into the specification language was a way that I could now completely disconnect the specification from the model. And all the information needed to execute the specification is inside of the specification language. So there's no other information needed. That is a walk of the graph. So that breaks down into 3 parts, and you can clearly see each of those 3 parts. They are pretty simple in this example. You've got the given, which is the school. The matches, this has only one match, the match being the unknown label course and the condition that the course school is equal to the school. And then you've got the projection, which just says project out the course, because the result of this is a collection of tuples, where each of the unknowns is a fact within that tuple. This one having only one unknown. The tuple has only one element, and it's called course because that's the name of the unknown. And so here I just used the variable names that I declared above to kind of let you know these objects are in that collection. And so when you run it through the projection, that just picks that element of the tuple. You just get those objects.
Yeah.
So that's what that all means. But then we start to get into the different types of queries. So I started with the simpler of the two, which was the feed query. Which, as it happens, when I first implemented the specification language, I started with the read query because at first it was just a way to take a look at what's inside of the database, just a debugging tool. And then, oh wait a minute, this is really useful. I'm going to make this the protocol, and then backed into the feed query. So a query description is this intermediate step between the specification and the SQL, and so Jinaga.JS goes through this intermediate because it has to allocate some aliases within the SQL. So it's got to allocate an alias for selecting from the fact table and selecting from the edge table. And so sometimes those aliases end up in a from clause, sometimes in a join clause. Sometimes those joins are in the on clause, and sometimes they're in the where clause. So they end up in different places in SQL. So it was a lot easier to go through this intermediate step to get there. So for this first example, we talk about inputs, parameters, outputs, and edges, but we don't talk about not exist conditions because this one doesn't have any yet. So inputs, those are the given labels plus the identity of the facts that were passed in. So kind of scrolling back here to put this in context, courses in school is just the specification, and it can be described like this, but the actual execution of that specification is something like this, where we do the j.query for courses in school starting at a particular fact. So we're passing in a specific instance for those givens. So we've got that starting point, LPS, LPS for Frisco Leadership Prep School. That's actually where I volunteer. So the input is that parameter plus the hash of that fact, LPS Frisco. And then the parameters are a collection of objects that it's going to accrue over the creation of this query description, and those will become the actual parameters that we pass into the SQL query. So every time we want to put a hash into the query, we just put $1, and then parameter 1 is that hash, or an ID, $2, and $2 is that ID. So in this case, we end up with the parameters of being the fact ID of the type, or of the fact type ID of the type school, and the hash of the specific instance. So these two things should be able to identify a particular fact in the database. So once we have allocated those parameters, we put those parameter indexes into the inputs in this case. So we know that when we need to render out that that input, and these will end up in the where clause, by the way. then we could put the $1 and the $2, and those represent the fact type and the fact hash. This fact index, that represents the particular instance of the fact table, that particular fact alias. It ends up being F1 in SQL, and the first one has to be a from clause, and then the rest of them get to be join clauses. So this will end up being from fact as F1. So that's where that fact index comes in. And that F1 represents the label school. So SQL is already a language about tuples. That's really what the relational algebra is all about. It's a mathematical theory of relating tuples to one another, and so yeah, it's a really natural fit for this way of thinking about specifications. So yeah, just lean right into that, and then each from, each join is just represents a label within the specification. So then we get to the edges, and so the edges represent those relationships between two different labels within the specification. So the school is a label that's coming from the input, and the course is a label which comes from the match. And so course is an unknown, school is a given, and so it allocates a fact index for each of those two. School being the input gets fact index 1, which agrees with what we saw up here. And then course, being the first unknown that it sees, gets fact index 2. So once we allocate that edge, we give the edge an index, because that ends up being a join to the edge table. And so that alias for the edge table is going to be called E1. And so now we know the predecessor index, we know how it's related to F1, and the successor index, how it's related to F2. And then we have to allocate a parameter for the role ID. So that is this role defined in course. It's always defined in the successor with the name of school. So kind of tying that back to what we saw up here, that's what these arrows represent. So they're defined in the type course, and they have the name school. Or in the fact type diagram, defined in the type course, having the name school. And it comes from right here, that relationship. So now we have our edge. We've got the two fact aliases allocated, F1 and F2. We know the 3 parameters, so we've got our starting point, this fact type and this fact hash, and then we also know the parameter for the edge ID. And so finally we can say these are the outputs. So the outputs end up being all of the labels in the tuple. Outputs does not mean the projections. The projections can come after. In fact, for the feed, only certain kinds of projections are important. So we'll see that in the last example. But yeah, these outputs are all the facts in the tuple. Now, I say all the facts in the tuple. It does not include the inputs, which are, if you were to go through the the mathematics behind it, it's a lot easier to consider the inputs as being part of the tuple as well. That way, you can swap what's considered to be an input or a given, and things still just work out. But in this case, since we are targeting specification, we have separated the idea of input versus output. So those two taken together are all the facts in the tuple. So now we get to generating the SQL. And so we start with the select, because that's the way that SQL starts. And so we are selecting the outputs. And in the case of feeds, all we care about are the hashes. So a feed, as we saw in last week's discussion, gives you back a collection of fact references, which are the types and the hashes. Coming in, we already know what the type is, so we just need to output the hash. And if the client doesn't know about that fact, then it will then call load, and it will get the all the data related to it. So we don't need to select any of that for the feed. So it's just the hash, and then the bookmark. So the bookmark is a decreasing list of fact IDs in the tuple. The end. That's all I say about it. But for all the reasons that we talked about last week, that's the thing that works.
Yeah.
So this is pretty cool. This way of declaring an array in SQL and then using this sort function, this is something that's added to Postgres with a module. It's the int_array module. So in the Postgres setup script, I've got a line that installs the int_array module. So in SQLite, this might not be a capability that's available to you, but that's okay.
Because we don't need feeds there.
Because we don't need feeds, exactly.
Yeah.
Yep. So in the future, I probably will support SQL Server on the server side, and so then I'll have to figure out how to do bookmarks in SQL Server. But yeah, when I discovered this feature in Postgres, I was like, that's perfect. That solves exactly the problem I need.
Why would you like to support SQL Server?
Just to give people an option.
Okay.
It's probably not an option that I would use on any of my projects, because Postgres has is much more affordable, being an open source project, and
it's good and it's free.
Yeah.
So,
but yeah, I can kind of make up some reasons that people might want to use SQL Server. So they might want all of this, all of this Jinaga bookkeeping to participate in a transaction with, something that's a more traditional data store. So, for example, you've got a service that's just running a query, and then whenever a new fact comes in, then it gets notified, and then it processes that fact and writes out writes the projection back to the database. So you've got a persistent view model of the state. So if you wanted that to participate in the same transaction as the actual processing of the fact, then and updating your bookmark and all that stuff, then it would be useful to have that. If you chose to do that in SQL Server, it would be useful to have both of those in the same database. But that's not strictly necessary. If you've written that to be an idempotent operation, then they don't have to be in the same transaction anyway. But so haven't decided on that course of action, but I do want to leave it open. So yeah, we've got our select, and then we go to the from. That's just going to pick the first fact index that it has in that list of edges, which interestingly enough may not be F1. In this particular case, it ends up being F1, but since up here we allocated fact indexes for all the inputs, it's possible that you have more than one input. So you'll get F1, F2, F3 for your inputs. And then if you start off your edges by referring to the second or the third parameter, then you're going to have a relationship between F3, for example, and F4. And F1 will come in later in a later edge. So so that's one of the reasons for going through this intermediate step, is that first you can allocate those things. You don't have to assume that the first parameter is going to be the from clause. But then later, as you're going through the edges, you just pick out the given that is used in that first edge. So we've got from facted F1 with the alias F1, and then join to edge E1, because that's the alias that we gave that edge. So while we're doing this, we're just iterating through the edge collection. And then since this edge is related to F1 as the predecessor, which we can see from here, so it knows the predecessor index is 1 and the successor index is 2. So in parallel, while it's walking this this collection, it's keeping track of which facts it's already added to the query. So it knows that, or it considers that it has already added facts. Well, no, it actually does know that it already added fact 1 because it wrote out that fact clause, that from clause. And so it says, okay, I'm going to add the edge, join to the one that I have already added, and that one in this case was the predecessor. And then I've already allocated a role ID, so let's write that out inside of the join clause. And then add the remaining fact if it's not already been added. And I happen to know that one is the successor. And then just loop through until you're done with all the edges. In this case, there was only one, so you're done with the edges. And then you've got the where clause. So you go back to your inputs collection and you say, all right, I know that I've got the, for each input, I only have one. This input has the fact index 1, so F1. And then I've got the parameters for fact type and fact hash, so those go in there. When I'm done with all the inputs, then I write out the bookmark inside of the where clause. So along the way, it allocates a new parameter, sticks that on the parameter list for the bookmark, and then the last parameter is for the page size. So that produces that beautiful SQL. Yeah, so as we talked about, I think that was last week, it might have been the week before. Yeah, I think it was last week we talked about how right now feeds are executed from the database. In the future, there will also be the option of executing feeds off of different kind of infrastructure components, such as Kafka.
So then it will be just the inverse that fills up the buffer.
Yes, exactly.
And so you will empty the buffer by using the load function with the bookmark.
Yes.
No, by
not the
asking first from the feed with the bookmark, and next loading the facts individual from the database. Yeah.
Yep, exactly.
Okay.
Yep. And so when that happens, the bookmark will no longer be a decreasing array of fact IDs. It will be whatever Kafka says is the bookmark. Whenever I say input, add this tuple to that topic, and then it says, all right, there's the read bookmark. Actually, I don't think it gives you the read bookmark until you start reading it. I don't think it gives it to you on insert, but that's okay. You don't need it. So yeah, that's the feed SQL. Now, the one that you're going to be most interested in for the client side is the result SQL. And for this example, it turns out being very similar.
Mhm.
But the big differences come in the later two examples. So those differences have to do with nested existential queries. Don't have an existential query yet, and also um, child projections. And we don't have one of those yet, but those are the next couple of examples. So in order to support uh, running projections, so that's basically the goal here is to get a bunch of IDs so that you can then load and get that data on the client. The result here is to actually get the results of those projections. So in order to run those projections, you need to actually have the names of those labels related to the inputs and the outputs. So that way, when those names appear inside of the projection, you say, okay, um, uh, that's that particular part of the tuple. So I'm just going to read the data from that one and run that projection. So as a result, we select not just the hash, but also the ID and the data. So data is a JSON object that has all the fields and all of the predecessors. So given data, we can actually just completely reconstruct the fact object itself. Um, the fact IDs are necessary because we are ultimately going to be using a result composer that we talk about later in the document to put the child and the parent results together. So the fact IDs help us to figure out which child result goes with which parent result.
Mhm.
So we've got the join, the from, join, and where clauses just as we had before. So those are very familiar. And then instead of doing the bookmark with the order by and the where it's greater than the previous bookmark and the limit, so you've got the paging. Here it just orders by all of the fact IDs. So in this case, we just had the one output, so it just ordered by that one fact ID. But this would give you a nice um, a nice way to iterate through multiple collections. So that you could say, here I'm looking at this parent. Now let me go through all the children. Now I'm done with these children. Let me add those to the parent. Go on to the next one. So that puts the query together like so. So it's interesting to talk about how many queries will be run on any given operation. So far with this simple example, there was just one query for the feeds given that specification and one query for the results given that specification. But that's not always going to be the case. As you have more complicated specifications, the number of queries that you need in order to execute feeds or to execute results will grow. Um, and the nice thing is that it grows based on the complexity of the specification, not based on the complexity of the data. So you don't have a select n plus one problem where if I have one school and I want to get all of its courses, so I run one select in order to get the courses, and then now I want to get details about each course and I do n selects in order to get the course. That problem doesn't come up because it's going to, in that case, run two queries, one for all the courses and then the other for all the details you want about those courses all at once, and then compose the results after they come back in memory. So there is no select n plus one, but there are sometimes multiple selects. Okay, and existential conditions. These demonstrate one of those times where you do have multiple selects. So let's make the model a little bit more complicated. So now, instead of a course, a school just offering courses, it also gives you the opportunity to delete a course. So we add a new fact type. It shows up in the graph as so. And then let's add an instance of course deleted for the course Math 201, which happened to be trigonometry. And don't know why I'm picking on trigonometry. It's a fine course, but I think probably because now that I know about the complex plane, I don't think in terms of trigonometry anymore. I think in terms of complex numbers. Things make a lot more sense. But
Anyway, they are only math courses
mm,
in the example.
yeah, oh, of course. What else would you offer to school? I don't know.
Programming.
Yeah, that's true. But that's just a math course too, right?
Yeah.
Okay. So, yeah, we've got a slightly more complicated specification. So, I've added a where not any clause. And by the way, when I was writing this, the very first thing that Copilot recommended was to put this inside of the any, which is perfectly acceptable. And then I was surprised when it didn't generate any specification, description, a descriptive string. It threw an exception. I was like, oh, I did not implement the SQL or the link parser to accept an any that takes a condition. So I need to go back there and add that. But so yeah, there's lots of different ways you can add this condition. In this case, I chose to add it as a lambda inside of type. It could also be a lambda inside of any once I get that implemented, or it could be an additional where clause just on that particular collection. But no matter how you write it in .NET, it ends up looking like this in the specification language. So same specification as we saw before, plus we've got the not exists, and we give that that new label here a label deleted, and relate it to the course. So because it's inside of an existential condition, this doesn't end up being part of the tuple that that we want to that we output, and so deleted could not appear inside of the projection function. Especially in this case, since it's not exists, there is no deleted fact for the projection, so it wouldn't make sense. But even if it was an exists, there wouldn't be an instance of course deleted that would show up in the result tuple because there may be many of them. It's just at least one exists, and so it's just a constraint on the course, and the course is the only thing that comes out in the tuple. So we run that, and we get just 3 courses. So you'll notice that 101, 102, 301 are here. 201 is absent because that's the one that was deleted. So that's going to produce a new set of feeds and a new set of results. So let's take a look at the feeds query. And the thing to recognize is that there's a pre-processing step which is done in core, so that it doesn't have to be done by the by the storage implementation. So you're not going to need to write this step inside of SQLite, but there's a pre-processing step that takes that full specification and breaks it into feeds. And the way that it does that is that it it dives into all of those existential conditions, and it actually pulls those labels up a level. So now you actually do have a tuple that has course and deleted, and in fact it projects them all the way out. So So now you've got tuples of course deleted that become a feed. Now, of course, the results in that feed don't show up in your actual query results, but they are evidence that the client will need in order to execute its results query. So in addition to that feed, which only gives you the deleted courses, it also runs a feed that I don't think I specify. Yeah, I don't write the other feed here, but it also runs another feed, which is in fact this this same specification. So selecting only the courses with this not exist query added into the mix. So so what I walk through here with the SQL generation is actually generating that other feed. This one here follows all the rules that we talked about already. It's just walking two edges instead of one. But now here is where we add in these not exist clauses. So in the previous example, this was empty. There were no not exist clauses. There were no existential conditions at all. And so in this case, it's capturing the not exist clause, and for each one, it just has the set of edges. That's all that's interesting to it. So no inputs, no outputs, and for the case of feeds, no child not exist clauses. And there's an important reason for that, which we'll talk about in a second. So all we've got are the edges. So we allocate a new edge index for the relationship between deleted and course. It's referring to the predecessor course, which was allocated the fact index 2. And now it allocates a new fact index for 3, that is the deleted fact. Allocate a new role parameter. Put that deleted course role into that parameter list, and then generate the SQL. The part that now is different is now it gets to the not exist clause. So it walks that collection while it's generating the where clause. So for each one of the elements in that collection, it spits out and not exists, and then does a select one, because we don't care about the actual values in there. We just optimize by selecting the constant 1. So then we have to start with a from, and so in this case, since the fact index has already been emitted outside, it outputs the from the edge index. So let's start with the edge, and then we can join in the fact indexes that have not yet been written. So it knows that one is a successor, so it joins based on successor ID. And then it writes out the where clause, which is now where it can relate it to the things that were defined in the outer query. So now I know that I'm related to F2, which was already written out. Remember, it's keeping a kind of a log of what's already been written to the query. It says, okay, F2 is already in the query, so it doesn't end up as a join. Instead, it ends up inside of the where. And then we add the role parameter to it. And that gives us this beautiful SQL. So the important thing that I said we were just about to talk about, why not exists does not have a child collection. Why can you not nest not exists inside of not exists? And the reason for that is that we are talking specifically about feeds. So there's a cardinal rule of feeds that if somebody has already read to a certain point in the feed, if they continue from there, they're not going to miss anything. So you'll never insert anything into the middle of a feed. Now, that doesn't keep you from removing things from a feed. In Kafka, for example, there's an operation called compaction that will remove things from a feed once Kafka determines that a later element of that topic makes the previous element redundant. So it's not important to know about the previous. So this is that same idea where this not exist condition makes knowledge of this previous course irrelevant. It doesn't matter that you knew that this used to be a course. We can take it away from the feed as soon as we see that it's been deleted. But if there's a restore fact, which is a not exist delete where not exist restored, then you've got this nested not exist clause. It would have the effect of putting that course back in. And we can't allow that because you've already read past that point. So we don't generate any SQL past the first not exist clause. And that's for the feeds. For the results, it's different. It's different in two ways. For the results, we capture all existential conditions, not just not exists. So if you have an existential condition that says, this, where, let's see, that's not the interesting one. There's the interesting one. So if we didn't have the not here, so show me all the courses where there exists deleted. Maybe I'm rendering the recycle bin. So here's all your deleted courses. So you can pick one and restore it. So in that case, the feed actually just flattens that down. So we don't need courses where exists deleted because we are already rendering this flat feed, which has all the courses that have been deleted because there's a tuple that satisfies that condition. So that's why feeds only are interested in the not exist clause, and they only go one level deep. But with results, we capture all existential conditions, whether exist is true or false, and we allow deeper existential conditions. Such as if we do the restore. So I can restore a deleted course. Then, well, let's go ahead and restore trigonometry because you know what? These kids need a full education. And so you've got where not any, and here I kind of expanded that out to its full form, from deleted, where deleted is course, where not any restored. And so we get not exists, and then a deeper not exists. So running that against the data that we've got now gives us back all 4 courses. There's 201, and that gives us this set of existential conditions. So we have a not exists deleted course, the same structure that we saw before, and then this has a child existential conditions not exists restored deleted. So that relates fact index 3, which we allocated up here, to fact index 4, which we are now newly allocating. And that gives us the SQL that you might expect, where we nest the and not exists inside of the outer and not exists, but produce that in exactly the same way that we just talked about.
Yeah.
So output the where clause in order to join it to the fact that was allocated up here, just like this where clause relates it to F2, which is in a join up here. So it's kind of cool how it turned out that all of these rules about generating the SQL just kind of built on top of each other, and uh, and now I can just talk about, hey, this is what's different when you encounter this type of query. And so yeah, the last type is the child specifications. And so that is what happens, for example, when you've got information about each course that you want to output. So you've got the course name, which we have as another successor of course. Of course. So in this case, let's go ahead and allocate course names for each of our 4 classes. And so we just have that structure here. In this diagram, I didn't output the course deleted, course restored. Those facts are still there. I just didn't list them here. And furthermore, they're not used in this specification because I wanted to simplify this and just focus on the child specifications and not talk about the existential conditions anymore. But you can combine the two, and they work together the way you would expect. So here in the link, we're going back to this very simple from course, where course school is school. But now, rather than just selecting the course, we are selecting this this anonymous object with an identifier and names. This is the child specification. So we just go back to from name in facts of type course name, or course name equals course. So refer back to the label we allocated there, and select name.value. So that produces this child specification inside of the projection of the outer specification. So for each tuple that comes back, being a single course, it's going to, well, I'll say it like this, even though that's not what it's really doing. It's going to run this specification and select the name. If it actually did that, you would have select n plus 1, but that's not what it actually does. Instead, it kind of flattens those out and gives you a set of parallel queries to run.
Mm-hmm.
So
And there we have a limitation of the renderer, where it gives the system link enumerable.
oh yeah, yeah. So yeah, this is an enumerable thing of type string. I don't know what it is, but yeah. But then, yeah, here it actually renders out, oh, this is the array containing the string algebra. This is the array containing the string geometry. And it contains the string because this projection was name.value. So not the name fact itself, but the value field within that name. So so now when we do the feeds, the SQL is produced just the same way as we saw before. There's nothing new about the SQL. What's interesting is how it splits that specification into feeds. So it's going to run one feed for the top level specification that gets you the tuple including the course, and then it's going to flatten the child specification into that top level one. So that gives you a tuple of course and name. So the reason it does that is that if you have a course that you don't yet have a name for, you still want that to be returned. So this should still give you, for example, the course identifier. It's just your names collection will be empty. So this is kind of the equivalent of doing a left join in SQL. Although I don't use left joins in the SQL generator because this was a lot easier to reason about. So yeah, it runs 2 separate queries, one to get you the courses, and this is where those fact IDs come in. So you've got the fact IDs for each of the courses, and then it runs another query to give you the course name tuples, and then it can walk them both in parallel, collect up the names, and add that array to the courses. So so that's the interesting part of the feeds. SQL generation just as before. The interesting part for results is that that it does that result composer that I just talked about. So uh, so where it's got those two specifications, and then it walks them in parallel. So the result that you get is a yeah. So you've got this first the first query just gives you the list of the courses. The second query gives you the list of all the course names, and then when you run the fact composer, that's what puts them together, and each course gets its own collection of names. In this case, because I set up the data in this way, each one has just one. But as we've said many times before, there's no way to prove that there will only be one. So it's always an array.
Mm-hmm. No, this is a very nice build-up of starting with something not so complex and going to a more complex specification.
Yeah, I think that worked out pretty well. So yeah, thank you for the recommendation. So when we were talking about this, you mentioned you would like to see some diagrams of what does the data look like, what does the model look like, and being able to do that inside of um, Jupyter
Jupyter.
or .NET Interactive notebooks was
Mm-hmm.
it was a big help. So I think that all worked out.
Yeah, the only thing that is not generated automatically is the SQL itself in
Yeah,
Jupyter.
yeah,
Um,
So I had to run the debugger and
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 paste it
copy
in.
that stuff. So yeah, but I had unit tests already set up, so I could just debug those unit tests, copy that stuff out. So there we go. Yeah, conclusion just kind of goes over the difference between feeds and results.
Why did you wait so long to make this document?
Well, I didn't have this system fully formed in my head until I saw it working. So yeah, that's kind of the downside of test driven development is that you can't fully explain how the thing works until it works.
Mm. And the amazing thing is the way it works, but also the tools around it, like .NET Interactive. Everything just fits into place.
Mm-hmm.
.NET Interactive combined with the render um, algorithms that you've written,
Mm-hmm.
uh, it's very nice that way. Um,
Yeah, yeah, I kind of like that. But yeah, it is making me while I was doing that, it was making me think. You know what? It would be really nice to add a little bit of a function here that would spit out the SQL, so I could just have uh,
mm,
that shown. The problem is that the thing that renders that SQL is part of the storage strategy, not part of the specification. So I would have to take the specification, give it to the Jinaga instance, tell it to use your storage strategy to do this thing, and then give me back the results, which is
mm,
just for the purpose of displaying them on the screen, kind of kind of strange.
yeah, no, indeed, that SQL is dependent, whether it's Postgres
Mm-hmm.
or SQL Server.
Yeah. But all right. So yeah, I think once we've got the SQL generation for Jinaga.net, we'll be able to to start building up some examples. Try Jinaga.net with with Blazor. Try it with Maui, or
Mm,
even just try it with ASP.NET. Just do something something simple and find where the holes are.
Um, I finished that SQLite.net and then I go the Maui direction.
Okay, yeah,
Um,
yeah, because that'll be the direct course
yeah,
to updating your mobile app.
yeah. Um,
Excellent.
but I find it amazing how you used it in a simple way, just for the replicators.
Mm-hmm.
Because for DWS, if you look at the model, it's very complicated.
Yes.
But if you look to the replicator website, of course there will be facts added.
Mm-hmm.
For the moment, it's a very simple model,
Yeah. Yeah.
and it already allows you to make something.
Mm-hmm.
Um,
Yeah. Yeah. That's part of what I'm just really enjoying about this project is that just like I was talking about with this SQL generation, each thing is able to build on what's come before, um, and that's a result of this not being domain specific. It doesn't know about the problem domain that you're solving. When you write domain specific code and you create your own tables, you create your own APIs. Um, you don't really have that opportunity to build on what you just created because now you're on to creating a different thing. It says, oh, okay,
yeah,
I'm going to follow the same patterns, but in this case, the patterns aren't quite right, so I have to change them a little bit. It's like, well, no, let's just go ahead and reason through all of the possible patterns that are defined by this set of axioms, and then just implement it once. Build it all on top of each other. Once all the gaps are closed, then all your domains are covered.
this is truly universal.
Yeah, I'm looking forward to getting this out into the hands of
Mhm.
developers that can just take this, start writing simple specification, and then everything just work. I mean, it's gonna
Yeah.
be awesome.
Okay, let's get going to try that.
Excellent. All right, so yeah, next week you'll have the SQLite done.
I hope so. I hope so. Fully done it will not be, but uh, maybe finally have the complete cycle. Because for the moment we have the SQL generated,
Mhm.
but it was still having troubles with that product to store it in SQL itself. But
Mm.
let's continue to work on that.
Yep. All right, sounds good. Well,
Okay,
until then,
Michael, thank you very much for all this explanation. Um,
my
it
pleasure.
brings me closer to the solution.
Excellent.
And see you next week.
Yes, see you next week.
Okay, bye bye.
Bye.